computer-related facilities that appeared in during the pandemic, but on the other end of the story as a listener. So I learned that you can go running or biking while listening to a talk. So that I kept a bit in mind while preparing the slides. Let's see whether I managed to do that. So that means I'll have to do a lot of talking. Right. So my aim is to explain something that I've been interested for, and I've been looking on and off for more than 10 years, these geometric structures, gamma structures. And which, because of that was completely independent of my interest of Poisson geometry, but because of the work in Poisson geometry, both in terms of structure as well as tools, actually managed to, I think, at least understand and get whatever I wanted. Of course, I want more now, but at least what I wanted originally, I think I'm more or less there. So I'll try to give an overview of that. And yeah, you see here 3 nice PhD theses from Utrecht University. So that's something that along the time contributed to this. 2 of them, of Maria Salazar and Francesco Catafi, were more or less part of this project. The one of Ioan Mărcuț was completely independent, but that's where the tools that I learned turned out to be useful. Okay, so my plan is to go do an overview on the geometric structures, what's the framework that I work in, and which are the main questions I have in mind. Then I'll mention some of the sources of inspirations. Most of them are coming from Poisson geometry, symplectic geometry, cons theorems. So these will be used to tackle these questions. And then I'll return to the original questions, and I'll explain very briefly our approach and the results. And here I mentioned some of the old literature. I mean, when I said that I've been interested for more than 10 years of this geometric structure, basically I've been staring at many papers. I think if I put the papers one over the other, it's about 2 meters of papers, which looks very interesting, but they seem to be extremely complicated. And my aim was only to understand those. So somehow, of course, with understanding, also new results come in. But my aim was really to understand what was happening. Okay, so let me start. So geometric structures, the framework for geometric structures starts with background Lie pseudogroup, by which I mean, so first of all, by a pseudogroup on a space X, on a manifold X, it's a collection of yeah, already the first mistake, Rn is X. So it's a collection of diffeomorphisms between opens in X, which are, the collection is group-like. So it's closed under composition and taking inverses of functions of diffeomorphisms. And then it's sheaf-like property that it says that if I restrict an element of gamma to a smaller open, it's again in gamma, and I can also glue such things. So that's the pseudo-groups that are somehow part of the model that govern geometric structures. And there is this Lie condition, which is a smoothness condition, which one way to put it in an imprecise way is saying that the elements of gamma are solutions of a system of PDEs. But the precise, simpler way to put it is that if you form the jet space is jk of gamma for all k's. So I just put together all k jets of elements in gamma. So that's a subset of the space of all k jets from X to X, which is a manifold. So I'm requiring this to be submanifolds. So you get the tower of jets, 1 jet, 2 jets, and so on. And on top of everything, it's germs. Okay, and once you have such a Lie pseudogroup, you can talk about gamma structures on arbitrary manifolds M. So the pseudo group gamma is over X, and now I'm taking another arbitrary manifold M. X, you may think it's Rn, for instance, as a model space. So given a pseudo group gamma on this model space X, we look at gamma atlases on M. So they are like in the definition of manifolds, just the charts now compare opens in M with opens in the model space X. There's not a big difference. The main thing is when you look at the change of coordinates, right? They go between opens in X, and they have to belong to gamma. So the outcome, if you take equivalence classes of such atlases, gives the notion of gamma structure on M. And this is a very general framework that allows to handle geometric structures. And based on examples, in the next slides, I will look at the example, but based on examples, one of the first questions that comes to mind, that pops up, is what are almost gamma structures? And this will come up later as well, but intuitively, let me just say that almost gamma structure is just shadows coming from the jets of gamma structures. I mean, you look at gamma structures, you take K jets of elements in the atlas, and you look at that structure, forgetting that it comes from a gamma atlas. And yeah, that's best seen first in examples. So I'm describing structures, almost version of the structure, and the integrability condition which distinguishes the two, right? For symplectic, you have almost symplectic structure, which is like symplectic, but d omega equals 0, it's missing. For foliations, the almost version is distributions, and the integrability condition is Frobenius evolutivity. For complex, it's almost complex, and you have the Nine-house tensor vanishing. Then you have Riemannian metrics. These are the almost versions, and the structures themselves are less interesting. And these all fit in a general class and a general framework of gamma G structures, where G is a subgroup of GLN. And in that context, it's understood that there are certain integrability tensors that come in to distinguish the two. Right. So here, gamma G is, so for a subgroup G of GLN, there is an induced pseudo group gamma G on Rn, which are made of all diffeomorphisms between opens in Rn, for which the Jacobian is in G. For instance, when G is O of n, right, we are talking about, symplectic group, we are really talking about symplectomorphisms. And then G structures, classically is defined, the notion of a G structure of manifold is defined as a G reduction of the frame bundle of M. So that's what is known. And so if you look back at the question 0, what's almost structures, at least for this pseudo group gamma G, almost gamma G structures are G structures. But somehow this is the best, more or less, the most that has been understood. And that, now looking backwards, that's due to the fact that the way we understand it is the fact that these gamma G's are transitive, right? Any 2 points are connected by diffeomorphisms in gamma G. And if you have seen the definition of Lie groupoids, you know that Lie groupoids are basically the same thing as principal G bundles. So whenever you have transitive Lie groupoids, you can avoid using groupoids by using Lie groups and principal bundles. So that's the reason these were best understood back then, when maybe groupoids were less understood. Okay, and then the main questions in the context of general Lie pseudo groups. First of all, is what I mentioned. What does it mean to have an almost gamma structure for a general gamma? Then, of course, you would expect some integrability tensors, which ensures that an almost gamma structure actually comes from a gamma atlas, so it's a gamma structure. And then hopefully there are integrability theorems in which you can get rid of the almost, saying that if the tensor vanish, then indeed you have these nice gamma atlases, like in the classical Darboux, Frobenius, or Nylander-Nirenberg theorem. Right, and the ideal integrability theorem, which is certainly not true in such generality, is that an almost gamma structure whose integrability tensor vanish is integrable. But we like to see the minimal conditions added to this.
Zamiast teraz spróbuję coś poczytać.
Sorry? Well, is there a question?
I think Pavel.
Sorry.
Yeah, thanks. Yeah, Marius, go ahead. I think probably Pavel just didn't mute his mic.
Okay, I'm going to go through some of these sources of inspiration and background, which allows us to tackle this problem. So these are some boxes that I want to touch upon. So first one is the PDE.
Maybe I have one quick question. At the beginning, you have these model spaces X,
yeah,
which are not necessarily Rn. So what should one have in mind other than Rn?
It's not, I mean, it could be Rn from which you omitted some points because your diffeomorphisms are not really defined at certain points. I think with the generalization that come out, you may think that your X is a Poisson manifold, but then you look at more interesting pseudo groups in a more generalized sense. But really, for the purpose of this talk, just think about Rn. It's just, I'm not going to use that it's Rn, and it would be just a heavier notation, have it Rn all the time. But yeah, Rn is already enough for a lot of interesting stuff.
Okay.
Right, so I need a framework of PDEs which is well suited for what I'm trying to. I mean, you see, PDEs, systems of PDEs. There are so many ways to handle them, and there are really lots of schools and different schools. And what I'm describing here is something which, in some sense, is known, but is the simplest framework that allows for looking at PDEs. I mean, you see, with existing frameworks, what you can do is have a very simple framework, but then to put in some very interesting PDEs into the framework may require a bit of work. Or you can have a framework that is immediately suited for more complicated examples, but then the framework is more complicated. Right? So here I'm going to the one of the extremes in which the framework is very simple. And I'm just giving this in an example, but this goes all the way back to Cartan. So I just write down a PDE here, and I'm reinterpret it as follows. I'm looking at a bundle R3 with coordinates x, y, z over R2 with coordinates x, y, and z, I'm interpreting it as a section of this bundle. And then you go to jets. So you go to first jets of sections of these bundles. So this will be R5 with coordinates x, y, z. Then zx, which is a coordinate that you think about as being representing partial derivatives with respect to x, and then zy, but these are just variables in R5. And then inside R5, you have this specific subspace defining the equation, which says zx plus zy equals z, right? And now if you think a little bit, z is encoded, as I said, in a section f of this bundle. But the section is any function z, right? Now a section has a first jet, which sends xy to x, y, f of xy, partial f over partial x, partial f over partial y. And now the condition that is a solution of the equation is that this first jet takes values in the subspace E. And the key idea of Cartan Cartan's trick was the fact that there is actually a one form on these jet spaces, on E in this case, which is dz minus dx dx minus zy dy, one form on this space, so that if I take an arbitrary section f tilde, it arises as a J1 of f if and only if it kills theta. Right? So you have these forms which allows me to read back when a section of E comes actually from a solution of the PDE. So in this way, you can just forget, you can just concentrate on the blue things here. You can concentrate on the blue things. So you have a manifold, we have a vibration over M with a one form, and the solution of the PDE are sections which are tangent to that one form, which kill that one form. So this really goes back all the way to Cartan when he really introduced the exterior differential calculus, for more or less for this reason. And then our general framework for, I call them PDE bundles, is looking at this blue thing here and thinking carefully which are the main properties of theta, of this Cartan one form, that really matters. So this is the abstract notion. PDE bundle is a vibration E over M together with a one form with certain coefficients, satisfying certain conditions of transversality, vertical transversality, and vertical involutivity. So these are the properties that you realize after a while that is what really matters. In the general context, you can talk about solutions of these PDE bundle. These are sections which kill theta. Right, so this is the general framework. And yeah, of course, this is related to more or less directly to many of the existing frameworks. I'm not going to discuss that here, but we can at least apply to the general principles that are well known. They just look a bit simpler because you have this, you get rid of the reference to jets. And you see, these, yeah, I should have said this, I used as a motivation just for jets, but of course there can be systems of PDEs of arbitrary orders and jets of arbitrary orders, but they all fit in this one single framework, right? With PDE bundle, you don't have to do something extra, right? So I think the existing theory gets quite a bit cleaner or less technical. Here is a brief summary of the standard theory. One standard tool in studying these PDEs is the notion of prolongations, in which you basically take your system of PDEs and you add the new equations obtained by taking derivatives of the original equation. So you get then a new system of PDEs and then a new PDE bundle, the prolongation of E. So the prolongation of E is obtained by adding the first order consequences of for the PDE encoded by the original bundle. You can keep on going and continuing this intuitively, and you get an entire tower of PDE bundles, which, if you think a bit what it means, it's better to think about what happens at infinity. If you look at the fiber, these are all bundles over M. So if you look at the fiber of this E infinity at the point X, you see that it's precisely the set of formal solutions of your original PDE around X. And what these EKs do, the fiber at the point X are really formal solutions up to order K, right? So that's something that you often encounter when you solve your PDEs by power series first, right? And then, yeah, now this, I think, I mean, PDE is a very general term, but everyone has solved some kind of PDE, some coming from mathematical physics, some have seen it in geometry, but especially in geometry, that's something that you often do. You try to solve it by power series, so you try to solve your PDE formally, and then you see that at each step, either you can solve it, or very often what happens at each step, what comes out is a certain obstruction of a cohomological nature. So you very often have cohomologies that ensures that you can go higher and higher in solving formally your PDE. So that basically means that you go backwards in this tower. And then formal integrability, which means finding formal solutions. In general, they are controlled by certain tensors. I'm just calling them generally torsion of E. And they are sections of a vector bundle, which is of a cohomological nature. I'm not going to enter into details, but it's what's called the Spencer cohomology of the symbol of E. But it's important to realize that these are very linear objects. These are things that are easy to handle. And if you haven't seen this before, maybe it's good to have some type of example in mind. For instance, if you think of the integrability condition for an almost symplectic structure, d omega equals 0 as a PDE, and you start applying this machinery and you look at this bundle TKE, what comes out is the third exterior power of the cotangent bundle of N. And sections of that, it's where the integrability tensors live. Of course, is the differential of the two form, which is a three form, right? So that's how these cohomologies bundle looks like in examples. But you do have in full generality these tensors, which control the integrability, the formal integrability. Right? So you have the tower and distortions, sections of the Spencer cohomology. And then, yeah, there is this very subtle notion of involutivity of the original PDE, which means, by definition, the vanishing of these Spencer cohomologies. That's something that you do not need in order to achieve formal integrability. Distortions are enough to vanish. But if you require that the actual Spencer cohomology vanish, then the situation is more interesting, and you call that property involutivity of your PDE. And one reason that that's interesting, there are many reasons that's interesting, but one reason it's interesting is that you actually have existence of true solutions if the Spencer cohomology vanish. So involutivity implies integrability in the analytic case. So there's the big problem here, that you need to assume that all the data is analytic. But I think in the theory, the geometry of PDEs, this is the best known theorem to handle the existence of actual solutions. And of course, there is the big question that's one of the questions I had in mind. Is there a smooth Cartan Keller? And just looking at it like that, there are counterexamples. There is the famous Levy counterexample. But after a while, you realize that those counterexamples, they're counterexample to a very naive version of the Cartan Keller. And if you think about examples that come from geometry, where Nylander, Darboux, constant linearization, all those results hold also in the smooth case, you realize that there is actually a good statement, and there is probably a smooth Cartan Keller. I'm not going to call it a theorem yet, but it's I think it's waits on my desk after this project. Okay, then so there's the PDE box. Then let me see, how do I do with time? Not great. PDE, there's coils. Yeah, let's see. At least at this part, I feel I can go a bit faster. I hope that's okay. If I'm going too fast for someone, they just slow me down. So I'm using this language of Lie groupoids and what all we learned about them coming from Poisson geometry. So first of all, there is the notion of Lie groupoids, right? So that's it's like a Lie group over a manifold. You have on top a space G made of arrows between points in your manifold M, and you can compose them when they match. And on the infinitesimal side of that, you have Lie algebroids over manifolds. So you have like, that's like the generalization of Lie algebras and also of tangent bundles. So the main structures here is a bracket on the space of sections, like Lie bracket of vector fields, and an anchor relating this replacement of the tangent bundle A to the actual tangent bundle Tn. And what's important here is what we call the Lie philosophy, the fact that you can go from the global side, which I mean groupoids and whatever live on groupoids, to the infinitesimal side, by which I mean algebroids and whatever lives on Lie algebroids. And under very decent condition, you can also go backwards, integrate your objects, and obtain a one-to-one correspondence under mild conditions between global and infinitesimal objects. The point of the global objects is that that's where geometry lies. The infinitesimal objects, it's where it's easier to handle, and maybe it's also where you see some of the structures first. And this is already a very good example of that principle are vector fields that at least the way we learn it is starting from the infinitesimal side, right? So you have a vector field X. You get at this example by looking, let me go back. You look at the definition of Lie algebroids and you assume that A is the most trivial type of vector bundle. It's a line bundle, trivial line bundle over N. And then a row should send 1 to something. It's a vector field. And then the bracket will be determined by the axioms. You see, any vector field can be repacked into a Lie algebroid structure on the trivial line bundle. And when you integrate that, look at the groupoid that it comes from, right? There's the local flow of the vector field, right? Which is a submanifold of M times R, right? Arrows are pairs, a real number at a point X that you picture as an arrow going from X to phi X T of X. So the flow, the time T. And then the multiplication is the obvious one that follows from this picture, right? So that's a good example where you see the infinitesimal part and integrate it to the flow. And then the example, of course, that we all know and is related to our topic is the cotangent algebroid of Poisson manifolds, right? So whenever you have a Poisson manifold, you can turn the cotangent bundle into Lie algebroid by requiring that the bracket of two closed one forms, sorry, exact one forms is D of the Poisson bracket of the forms. So when you do that and you look at the global side, by integration, what you find is the notion of symplectic groupoids. So these are groupoids endowed with a symplectic form. And that's where we discover something very important, this notion of multiplicativity on the groupoid. Right, so this symplectic form is compatible with the groupoid structure in the sense that it's multiplicative. So that means that basically omega of G1 times G2 equals omega of G1 plus omega of G2, but you make sense of this equation for forms. Right? So you have to pull back everything to the space of pairs G1 or G2, which are composable. Right? So there is this multiplicative condition, which is simple, it's cohomological, it's quite conceptual, but I think it took us a while to realize the power of these multiplicativity conditions. These multiplicativity conditions are this global counterpart of things that we see infinitesimally. So these multiplicativity conditions really encode very important infinitesimal information that I think it took us a while to realize that that's the way to pack globally such conditions. And then still in Poisson geometry, there is this notion of moment maps and Hamiltonian spaces that comes in handy in my project, a source of inspiration, right? So you have, in this context, to degeneralize these usual Hamiltonian spaces by replacing the Poisson manifold M, the dual of a Lie algebra G by a general Poisson manifold N, over which you have a symplectic groupoid. And then again, there is a multiplicativity condition expressing the compatibility between the form on G and the form on the Hamiltonian space S. So again, multiplicativity, it's a nice way to pack something that on the infinitesimal side you see as the moment map equation. Right? So in this Lie theory, Lie philosophy, you see moment map equation on the right-hand side, and you see this multiplicative condition again on the left-hand side, encoding the compatibility between the symplectic forms of G and S. Okay, and then the other box that comes from Poisson geometry and has nothing to do with the rest is Kahn's linearization theorem, and that's something that was conjectured, I think, by Alan, was proved by Kahn, and now speaking for myself, it was explained to me by Johan Merkutz. So for me, when I say Kahn linearization, and I refer to the proof of Kahn's linearization theorem, it's always this piece of your notes that I'm looking at. But anyway, the situation, this is something that is easy to explain the statement. The proof is the difficult part. So you are in the situation that you have a Poisson bivector on Rn, which vanishes at the origin. And when you linearize it at the origin, you get a Lie algebra. And if the Lie algebra is semi-simple of compact type, then your original Poisson structure can be transformed into the linear Poisson structure corresponding to the Lie algebra G. And you can put this into the following setting of some kind of non-linear complex, non-linear sequence, where you go from diffeomorphisms of Rn to bivectors on Rn by associating to phi star of pi lin G of this linear Poisson structure. And then you can go from bivector to three vectors by sending pi to pi bracket pi. And we are really trying to prove that if I have this pi, which goes to 0, so it's Poisson, then it will come from the right-hand side. So in some sense, we are looking at the exactness of this complex. And if you linear, I mean, of course, this is infinite dimensional, but you can just formally linearize it, and you see that it's this is a part of the DGLA, right? Diffeomorphisms give you vector fields, and then bivectors, three vectors, and what you get here is the Poisson differential, and that's part of a DGLA. And as a general principle, you hope that if this linearized complex is exact, then the original nonlinear one is. And the key property of this DGLA is that, well, exact is not enough, but what happens is, because of the assumption, so that's where the assumption semi-simple of compact type comes in, that says that this linearized complex is indeed exact, but it's exact in a way which is controlled analytically. So you find homotopies going backwards, in which you can have loss of derivatives, but in a controlled way. That's the meaning of tame. So tame is well-behaved analytically well-behaved homotopy operator. And once you have these, the rest is Nash-Moser that they can implement to inductively construct solutions of the equations that arise when you check exactness of these complexes. And the loss of derivatives is taken care of by smoothing operators. But that's where I go to the thesis of your notes and I just look at the steps. And but the structure is here. So that's what matters, is the structure of DGLA and these tame homotopes. Okay. So these are the boxes that I need. So now I'm returning to the original structures and questions. So first of all, the first ingredient that comes in for us to study pseudogroups and geometric structures is the notion of Fafan groupoids, right? Which is now motivated by this example, which arises from pseudogroups, right? So if you have a Lie pseudogroup gamma over X, you can look at this space of k-jets of the isomorphisms that belong to gamma. But this is clearly a groupoid over X, right? Because the k-jet of diffeomorphism at a point X has a source, which is the point X, and has a target, which is the diffeomorphism applied to the point X. And you can compose diffeomorphisms within gamma, hence you get a multiplication on these groupoids. So these are really Lie groupoids. This is another way of saying that the pseudo group gamma is Lie, that this JK gamma is a Lie groupoid. And what we learn from this PDE box is that on these jet spaces, there are these Cartan forms that come in very useful. And the key remark is that these are multiplicative. These are multiplicative in the sense that arises from similar to multiplicativity of forms on symplectic groupoids. And furthermore, you can recover gamma from this structure by as bisections of this groupoid, which kill the Cartan, this Cartan form. So really, they are solutions, bisections which are solutions of the original theta. So based on that, that's the general notion that we play with, is the notion of Fafan groupoid. So it's just a groupoid G over X endowed with such a one form, an abstract one form, which makes the source map over X into a PDE bundle, right? In the sense, the general framework, I said, the PDE bundle, it's a bundle with the one form. We satisfy these conditions. So the source has to be a PDE bundle and theta has to be multiplicative. So I'm appealing to those boxes to write down the conditions on G. And once you have a Fafan groupoid, there is this interesting class of bisections of the groupoid which kill theta. These are called the holonomic bisections. So this will replace the pseudogroups. Instead of pseudogroups, we'll consider Lie pseudogroups, we consider Fafan groupoids. It's a bit more general, but it's not only being more general, which is useful, but it's not only that, it also makes the theory, I think, a bit cleaner. We concentrate on what really matters. And we do something similar to the notion of gamma structures, right? So this was about pseudogroups gamma, and once you have a pseudo gamma, you can talk about gamma structures. So similar to JKF gamma for a pseudo group, you have JKFS for an atlas, right? You can just take k-jets of elements in a gamma atlas and taking the original point and the end point, the source and the target of a k-jet gives now two maps, one into X and one into M. And the fact that the change of coordinates stays within gamma, it just means that when I compose k-jets on S to k-jets of gamma, I get an action of this groupoid of k-jets to the groupoid of k-jets of the atlas, right? So you find yourself into a situation which is very similar to what you see in Poisson geometry for Hamiltonian actions. And yeah, you can wonder now, in what sense are these canonical Cartan forms of k-jet bundles compatible? Well, it's precisely in the way you see it in Poisson geometry. There is a multiplicativity relation between them. So it's clear what the relevant notion here, right? You start now looking at action of such Fafan groupoids on manifolds endowed with one form. And you require that the map becomes a PDE bundle and the action is multiplicative. Right? For instance, if P was G with the original theta, we're just saying the condition of being a Fafan groupoid implies that this left action of G on G satisfies these conditions. And when this sits over a manifold M and this P is a principal G bundle, you talk about G structures on M. And now looking at this concept and knowing what we know from Poisson geometry and symplectic groupoids, there are lots of things that you can predict. There are Morita maps, there is Morita theory, all that, and it all works. But I'm gonna skip that. But I just want to point out that whatever we know from Poisson geometry really tells us what we should do. Also, the moment map condition. Now, if you look at the moment map condition, here there is no moment map condition. Well, there is this multiplicativity relation that we know that it encodes a moment map condition. So when you go on trying to prove things infinitesimally, you go to Poisson geometry and get inspiration from there to see that there should be some moment map equation, which is of infinitesimal nature and which is equivalent to this multiplicativity condition. So all the Poisson geometry in the background is like a light that shows you the way. And now let's go back to the original question. So first of all, the answer to question 0, it's tautological because we built everything based on these examples coming from pseudo groups and gamma structures, right? So by definition, an almost gamma structure up to order K on a manifold.
It's 18 hours.
Sorry for that. So an almost gamma structure up to order K on a manifold M is just such a structure for these Fafan groupoids of K jets of gamma, right? And now this is very precise. If you think about Morita theory, this can be viewed as a Fafan Morita map from this JK gamma to M. And that predicts a bit what happens for transitive groupoids and explains why for transitive pseudo groups, everything can be reduced because of the Morita theory to Lie groups. But anyway, this is a precise answer to the original question. And then there are a couple of remarks which are really immediate one if you look at the definition, that the integrability of the almost gamma structure in the sense that it comes from a gamma atlas. So the integrability that we are really interested in from a geometric point of view, whether an almost gamma structure is induced from a gamma atlas. That's equivalent to the PDE integrability of this bundle over X, I would say. It doesn't make a big difference, but I like to think of the bundle over X. So this relates the original integrability to the integrability in the PDE sense for a PDE bundle. And in the transitive case is what I said, that you can get away with Lie groups, G and principal G bundles. And that's basically the theory of G structures and their higher order versions with higher jets. Somehow, I think that's the reason that all these 2 meters of literature on gamma structures and Lie pseudo groups is basically about the transitive case only, right? Because, yeah, I think Lie groupoids back then were known, but I think the theory was really underdeveloped. These multiplicative structures and all that was really underdeveloped. Well, it was not existing. It was not available. So, but when you go to arbitrary gammas, that's what you need. Right? You need these groupoids coming in. So it's the same, in some sense, it's the same answer like for classical G structures, but now you have to allow Fafan groupoids and principal.
May I ask you about this diagram, which is now on the slide? So those two thetas, right? These are two very different thetas. Is it right?
Yeah.
Like you have a theta on the left and a theta on the right. So
Yeah.
these are two thetas living on different spaces.
Yeah. Yeah.
Okay, thank you.
They have a similar role, but yeah.
Okay,
To
thanks.
make the notation simpler, I follow the principle, use the same letter, and it's clear where it leads from the context.
Okay,
But,
hopefully.
it should be a theta p, right? Any examples? It's all everything more or less comes by restriction from these Cartan forms on jet spaces. Okay, so that's the answer to Q0, and then Q1, right? Because of the remark, the integrability of the structure is equivalent to PD integrability. Q1, for Q1, I can go back to the PDE box and work in the full generality of G theta structure for a Fafan groupoid G theta. So you have that. I can apply the PDE box to P theta sitting over X. And very important, I want to stress that you take advantage of multiplicativity. And what happens, you should not underestimate this. When you do the PDE box, the spaces that you come across, they are huge. They are, it's not easy to handle them. They live over bigger and bigger spaces. But multiplicativity, because of the multiplicativity, everything is compatible with the groupoid, with the multiplication, then everything comes down to M and to X. All the bundles will live over the basis, and they will become representations of the groupoids around. And actually, in some sense, it's even easier to just go directly to this setting and apply the techniques of the PDE box right away, because it's simpler than applying the PDE box. But this serves as a guidance, the PDE box, right? But you have to work out and make simpler all the outcomes. So anyway, as expected, you get for an almost gamma structure, then integrability obstructions, which are certain torsion tensors, which, as I said, now these are sections of a vector bundle, but now the vector bundle is over M. It's not over some huge space. It's really over M. And this Spencer cohomology bundle, it's actually, in principle, depending on P, it's of a more universal nature. So you see, let me write this down, move to this. So it's induced from a representation, so a representation of the groupoid G. So over X, you have a Spencer cohomology bundle, which only depends on this model, G theta over X, not on M, not on P. It's something of a universal nature, right? It depends only on the original Fafan groupoid you start with. You have this representation of this groupoid G, and once you have this P, like for principal G bundles, for Lie groups, you can attach that representation as a fiber to P to get a vector bundle over M. So that's how these cohomology, Spencer cohomology bundles of the structure arise, by attaching to P this representation of G as a fiber. So it's really neat. It's geometric, the outcome. And then these are the integrability tensors which control inductively the formal integrability of the original almost gamma structure.
Marius?
Yeah.
Sorry, here I maybe haven't quite understood. How do you build those tensors? So you have this diagram, and now what? How do you concretely build those torsions?
Let me try to jump.
Mm-hmm.
This is for general PDE bundles, right? For a general PDE bundle, we have these torsions, which are sections of the Spencer cohomology bundles, which I didn't tell you how you build.
Okay, so just to make sure, so we're not supposed to understand how it works.
No, I'm not explaining that. I'm trying to. I think I mentioned here as an example, like symplectic structures, right? When you get things like the differential of a two-form as a section of the third power of the cotangent bundle. I think that's good enough.
Okay.
Going into this, I think it is really remarkable that in this generality, the torsions are controlled by a cohomology. But it's far from obvious, right? So indeed, that requires some work. And all I'm saying here, I'm applying that to the PDE. I'm applying that PDE box to this setting, to this Fafan bundle, to this PDE bundle P over X, and I'm simplifying the outcome due to the multiplicativity. So that's how they arise. And then moving to Q2. Yeah, so here we really need to make use of this Lie philosophy and make use of the infinitesimal counterpart of these Fafan groupoids. So you start with the Fafan groupoid G theta, and you have to work out, and it is not clear from the beginning what the infinitesimal counterpart is, so that there is a one-to-one correspondence between Fafan groupoids and whatever Fafan algebroids would be. But that was what turns out to be. These are, of course, algebroids, and the extra data is are some connection-like operators D that we call Spencer operators, the generalization of the classical Spencer operators, which satisfy an extra condition, which there is some compatibility between the bracket of A and the Spencer operator that I'm not writing down here. But there is this notion of Fafan algebroids. And once you have that, this connection-like operator D will have a symbol, which is, I mean, this is just order 1. So it will be a vector bundle map from A to some, let's say, some vector bundle T. And you have the kernel of that vector bundle map. You find yourself into a situation which is known in the context of PDEs. When you study the linear theory, namely you end up with a so-called tableau. But it's precisely it's very simple structure, and it's linear, and that's what out of what you construct this Spencer cohomology that enters as bundles, right? So the bundles, those which I said in principle, they are simple, they are linear, they are vector bundles. They come from the symbol of this Spencer operator. And then what's also not, it takes a while to realize, I mean, after you realize, maybe it's not so difficult to prove, is that there is a DGLA behind the entire story. Right, you see this Spencer-like operator goes from sections of A to one forms with values in E, so it's not very nice because you change the coefficients. So if you try to fix this and use only A as coefficients, you see that it actually can be done, modulo taking some quotients. So what you end up is with forms on your space, on your base, with values in the Lie algebroid, and the structure of DGLA. So this will be a DGLA. We'll have a DGLA structure. This is really the structure that it's analogous to what the DGLA that appears in Kahn's theorem. But this comes out. I can show you some formulas if you want, but it's irrelevant for now. So we're looking at the start of this linear complex, this DGLA, Spencer DGLA. And then similar, let's see, to what had in Kahn's theorem, there is a similar nonlinear complex let me see. To make the story short, the integrability of a gamma structure will then be equivalent to certain cocycles here being trivial. You have this nonlinear complex, which looks very similar to the one appears in Kahn's theorem, just that here there is a differential, there is the Spencer operator, there is a bracket, which is this bracket coming from the DGLA. So all the structure is really important. And what happens is that if you have a G theta structure as before, so first of all, the integrability of P, it's equivalent to the vanishing of certain nonlinear classes, canonical, they are completely canonical. They are based on choices, but the outcome is canonical. There are several because you see integrability, it's a local problem. So you have to look around each point, you have to find a chart. So around each point, you get another cohomology in the nonlinear complex. So the main question is whether this nonlinear complex is exact. And now you have all the structure that looks like what you have in Kahn's linearization theorem. You go to Ioannoutzis thesis and you apply the method there, fix whatever is different, and what you get is that the linear complex, if the linear complex is time exact, then the nonlinear complex is exact. So if you have the time exactness of the linear complex, you'll obtain integrability, full integrability. So that's if you want an instance of smooth Cartan-Keller in a specific case, but this I think is general enough to get a general smooth Cartan-Keller. Let me see how am I doing with time. I think I have 1 minute left, so I'm gonna stop here. Thank you.
Okay, thanks a lot. Yeah, please, questions or comments?
Yeah, I've got a question, Marius.
Yeah.
What example, first of all, I mean, it's very nice to have this thing that unifies what looks like they were different, different examples of integrability theorems. Does, for example, is Newlander-Nierenberg a special case of this theorem here?
Well, this, yeah, I mean, this reduces the Newlander-Nierenberg to proving that a certain complex on Rn is time exact. I mean,
I see.
Now, I didn't want to state that because that's not a theorem, but it's a conjecture, is that in the elliptic case, tameness follows. So you end up to checking exactness of something that you know. So reduces Newlander-Nierenberg to triviality in homological algebra, if you want, if you can call Poincaré lemma like that.
I see. So that you haven't checked in that particular case.
No, but I think we checked time exactness in that case.
Are there other examples that are kind of new, that new integrability theorems in contexts where they weren't already known? Or do you have examples of things that you're going to try to prove?
Yeah, I was mainly interested in understanding the known examples. Of course,
Sure. That's very interesting already. Yeah.
You get a much more general framework. So on my list is really going to these general pseudo groups, right? In which your pseudo groups are not collections of diffeomorphism, but a collection of bisections of a groupoid. And of course, the favorite ones for me would be Lagrangian bisection or symplectic groupoid, right? So you get there some very natural pseudo groups that were never studied, I think, right? So I have no idea what comes out of there. But then there are also, there are examples, you see, this theory that was known is really restricted to transitive case and to very regular examples. If you allow groupoids, bisections of groupoids, you can also handle things which look classical but weren't treatable by classical example. Like even when you have a group action G on a manifold, if the orbits are not of constant rank, then yeah, the pseudo group really in the classical sense down on M, it's very badly behaved. But if you think of the action as giving an action groupoid, and you think about bisections, that's really a nice like pseudo group which projects down to M on something badly behaved, but it can be studied up the groupoid level.
I
Right?
see. Mhm.
Even there, but it's, I think, I started calling this theorem a theorem, I think about a month ago. So it's too soon to like look at other examples.
Okay, more questions or comments?
I was wondering if I could just say the same thing that I always end up saying, Marius, which is that multiplicativity is really an instance of the Cartan equation for differential forms on a simplicial manifold, and recasting the theory of Lie groupoids as being about simplicial manifolds brings lots of simplifications. You don't have to introduce as many individual concepts. So I'm wondering if these notions on the pseudogroup side can be expressed in terms of maybe simplicial in manifolds or something, and differential forms.
Yeah. Yeah, I mean, that's something, yeah, I think that's a secret box in my mind. I mean, these simplicial things are also very useful. And in principle, I think things can be done. Technically, well, maybe more than technically. The problem is that, you see, if you have like actions of groupoids, you can return to groupoids by taking the action groupoid, right?
Right.
And now the problem is already when you have a Hamiltonian action on a symplectic manifold, when you take the action groupoid, what's the structure that you have around? I mean, it gets the extra structure on. You see, you can have a symplectic groupoid acting on something, but when you take the action groupoid, it's no longer symplectic groupoid.
Right.
That's the big little problem that you have to solve to implement this. I didn't think about this serious, but I think Alan.
I'm sorry. I mean, being a symplectic groupoid is a combination of two things. One is that you have a closed three form on the classifying space of the groupoid, and the other is that there's the two form on the morphisms has a non-degeneracy.
Yeah.
And that non-degeneracy can itself be expressed by combining multivectors with differential forms into a larger differential graded Lie algebra and looking at some Cartan equation there. That point of view has become very important recently in derived geometry, because you only have there non-degeneracy up to homotopies, and you have to express the whole tower of higher homotopies. So for what it's worth, there's a work of Kudavadian and Voronov, which are you familiar with, where they look at generalizations of Poisson geometry? Oh, it might be relevant. I don't know. Anyway, it's a great paper.
I take it as a hint to look into these higher.
Well, what I recommend is the paper of Pridham on Poisson geometry and derived geometry, because it's mind-blowing how things simplify and get more complicated when you go to derived geometry, but it really clarifies what it is that symplectic manifolds are.
I see. That may be cool. Yeah. Okay. Thanks.
Just a thought. Anyway. Okay. Thanks. Yeah.
Thank you. Any more questions or comments? I have a possibly naive question. So Marius, you mentioned those moment maps, right? And the moment map condition was some kind of instance of multiplicativity or action property, right?
Yeah.
And then how is it in this language, the whatever existence or uniqueness of moment maps do those problems also fall into the category that you consider, or not at all?
So the existence of, yeah, first of all, on the Hamiltonian side, on the classical side, I tend to restrict to Hamiltonian spaces, really, for which we don't have the moment maps. If you give up on that, and you see the analog of that, I think I'm in trouble. I have to assume the moment maps from the beginning.
Okay, then forget existence. What about uniqueness?
Well, it's kind of built in that it doesn't make sense to talk about the structure if I don't start with the moment map. You see, it's how do I mean, in this definition of structures, right? I start with an action of G on P.
Mm-hmm.
And part of the having an action is the moment map, right? So I cannot say start talking about an action if I don't talk about the moment map. Of course, you can start deforming. You can start deforming these structures, and among them, you can look at structures with a given moment map, with a fixed moment map. Yeah, these are things that can be done. They are probably doable. There is probably some very nice, non-trivial but doable DGLAs handling those kind of deformations. But now it is too early to have anything precise. I never thought about that.
Okay, thank you. And in the meantime, Ezra posted on the chart the link to the article that he mentioned and his question and comment. So any other questions or comments for Marius? Well, if not, look, thank you everybody for participating. Thank you, Marius, for this talk, which is actually the final talk of this season on Global Poisson. So we'll now have a break. I wish to everybody a nice end of the year celebrations, and hopefully next year will be more normal than this year, or at least it will be different in some positive way, hopefully. So I remind you that the next Global Poisson after the break, it will be on January 14th. And this will be a talk by Richard Melrose. So thank you again, Marius.
Thank you. Nice holidays to everyone.
Well, and thank you, everybody. Bye-bye. Have a nice break.
And thank you to the organizers for a great first year.
Well,
yes, indeed.
Yeah, thank you. And of course, we are very happy to have Nikita, who is helping us. So without him, probably this series of webinars would have not been possible. So thank you, Nikita.
Thank you so much.
Okay, bye-bye.
Everyone, happy holidays. See you in January. Bye-bye.